Okay, this wasn't mostly my idea. Most of the
Tell us all about yourself first. Tell us why, what for.
most of these ideas actually in raw form came from David Conrad, so I want to make sure he gets an act for that, or blame, or whatever. Okay, so I'm going to do the data plane portion of the talk, which is going to be for a half hour, and then Dave's going to do the control plane part of the talk. And I'm not going to talk about myself. Elliot and Noel couldn't be here, but these are the co-conspirators in this effort. So I'm going to talk about what is LISP, why do we want to do it, and then give you some protocol details. It'll be hard to get into nitty-gritties in a half-hour time frame, but I'll be available till Wednesday evening if people want to get into the nitty-gritties. I would love to. Devil's in the details, so we want to get all the evil out of it soon. Prototype and deployment status, and then a summary. So what is LISP? It's a locator ID separation protocol. Okay. The ground rules for the protocol is that we wanted to make it a network-based solution. Didn't want to change hosts at all. No stack changes. No major changes even to configuration files of the host as well as the site devices. And it was imperative that this be incrementally deployable. We think we could put this on top of the existing internet without any major architectural changes. We're using a lot of existing technology that's well known, so the benefits and the disadvantages of the various tools, various techniques we're using are well known as well. And it's address family agnostic. We think the solution could be used for IPv6 as well as IPv4. There's more urgency for IPv4, of course, but we have the same routing architecture problems in IPv6 as we do for IPv4, so we want to solve it for both. LISP actually separates location and identification from an existing IP address. That's basically what we're trying to do. Today, an IP address means who you are at the time you're logged in and where you're located. So we're going to try to separate that. That level of indirection can help in many ways. So an IPv6 address, for instance, you could actually split this 128-bit value into two pieces, a 64-bit high-order locator piece, which is in red. Throughout this presentation, as well as Dave's presentation, red are going to signify locator addresses, and green are going to signify IDs, or endpoint IDs, as we're going to call them. So you could split this address into the high-order 64 bits of a locator, lower 64 bits as an ID. And the idea here is that the ID doesn't have to change at all, but the locator can change as you move, whatever move means, and we'll get into details on that in a minute. So that's a locator, that's the ID. Now it's very interesting, we have this IPv4 address. Well, if you split into 16 and 16, it would clearly be too small to have a 16-bit EID, because you're probably going to have, in some cases, more than 65,000 TCP connections. Maybe not, but it gives you the feeling that it's too small. And clearly 16 bits of locator is not enough to put hierarchy into the system. So we have to figure out what to do with this small address. So what we're going to do is we're going to call what we see today, depending where you are in the network, a locator. And then we're going to go ahead and append another 32-bit address somewhere in the packet. It may not be contiguous, or I can tell you right now it will not be contiguous. Somewhere else in the packet that is going to be an endpoint identifier. What the level of indirection does, why should we do this separation? Well, we either want to keep the ID fixed and move the location around, or we want to do the opposite, maybe keep the locator fixed and move the EID around. We think the former is going to be more applicable. So by doing this, we're going to create two separate namespaces, an EID namespace and a locator space. And we will find out that we will piggyback off the existing address space depending where the packet is in the network at a given time. By keeping IDs fixed, we can assign fixed addresses that never have to change on hosts and add routers at a site. So we think a site that's running with a bunch of hosts and routers that are running an IGP, you don't have to make any configuration changes. We're going to add a new box that's going to be able to be LISP capable, but most of the boxes at the sites don't have to change. Very important for incremental deployability. Okay. What we're going to allow to do is change locators. We don't want to change EIDs. We want to make them pretty much fixed and maybe keep them latched to a host for the lifetime of the host or person or mobile device or whatever is an IP addressable unit. Now the sites can change providers without renumbering the hosts. and the host could actually move for different forms of mobility. So why do we want to do LISP? LISP can actually solve some other problems. It can improve site multi-homing. You don't have to inject more specific prefixes into the internet to be able to use your backup link. LISP will allow you to have all your connections to your ISPs being active-active rather than active backup. Right now, a lot of people use active backup and don't inject the more specifics, but they want better convergence. When the link goes down, their CE box goes down or the PE box goes down. So they really, most people in the experience I had building boxes for networks is we live in a day and age where we run active-active on most links. So active backup is kind of a thing of the past. So we have to get that to work without you injecting a more specific prefix, getting what you want out of the active-active link at the cost of everybody else storing this more specific prefix for you. That clearly won't scale with the number of sites that we have across the internet. So that provides some sort of ingress traffic engineering at the site. We believe by using this sort of technique you can do the same thing inside an ISP, and underutilized links between ISPs can be used as well. So this will reduce site renumbering or eliminate it altogether. We could also reduce the size of the core routing tables. If only the locator addresses, which map to topology, are consistent with the aggregation model in the ISPs, and nothing changes from there, we're going to have a good aggregatable system that can scale. The routing tables could stay reduced at the same time where there's ISP changes happening, people moving around, that sort of thing. And that's a good architectural model you want to go for. We can actually conserve IPv4 address space and as well as IPv6 because now locator addresses are not assigned to hosts. So you don't have to worry about allocating a block large enough to address all your hosts and oops, I made a mistake and now 5 years later I need another block. Well, it turns out that new block is not going to be in a power 2 chunk of your old block, so now this site has to inject two prefixes versus one. With the level of indirection, the only thing that is addressed are the boxes that have the attachment points, the directly connected attachment points to the service provider. So you can actually, an ISP now that's maybe getting address space can just allocate allocate less addresses per site. That's got to be a good thing. So we're going to do all this by architecturally creating a separate namespace, as I mentioned before. What provoked all this work? Well, a lot of us have known that this tool and toolbox called locator ID separation has been around for a long time, and we actually wanted to get deployed this time. We started this work 10 years ago. Nimrod was an effort to look at it, and it just never took off. So now we're going to actually say we're going to put some thrust behind this thing, and we're going to try to make it work. The problem statement was inspired. It's going to be exactly this week. It's 1 year ago that this routing workshop met. And we defined the problem statement. There were vendors and ISPs and host providers and enterprise guys that got together in Amsterdam and talked about this problem statement. It's documented in that first reference right there. Vince also has a document on stuff that he pretty much made his career on why the internet doesn't scale. And there's a lot of information at that second URL. Details. The internet draft that we currently have published is the design of the encapsulation and tunnel router placement. Okay, so that's giving you a sneak preview of what the mechanism is. We also have design for locator reachability. We're going to make a very important distinction between mapping an EID and a locator and the reachability of a locator. We're going to keep those decoupled and not part of the same protocol mechanism. And the data plane also has a data-triggered mapping service, but we also have control plane mapping service as well. And examples of that is cons, NERD, and RPMD. And Dave's going to talk about cons right after I sit down. So the control plane will be the ultimate scalable mapping service. So when you think about doing something that's incrementally and you don't want to change hosts, you have to put these middle boxes in the network to be able to give you this level of indirection. Well, what you can do is in something like GSE, you can actually rewrite those IPv6 addresses, the locator part of it, or you could actually put another header on and use the addresses on the outside. Those two schemes are called map in cap versus a rewrite or a NAT. So I'm calling it in this slide map in cap versus NAT. So the LISP model is very much a map and in cap scheme. where you have this protocol stack that's running on the host. You see the layers right there as we know and love. And then what you do is you put in another network layer, and the host stack will go ahead and build the IP header. Let's see. Am I going to be able to use a pointer? Yes. Can everybody see that pointer? Yes. This network layer here is built by the host stack, and the IP addresses that are inserted there are the IP addresses that a host uses today. They're basically addresses you get from DNS or you type in a command line. We're going to call those EIDs, but they're just a 32-bit address. What we'll then do is we'll have some box in the middle put a new IP header on. It's just a regular tunneling router that will do that. And what it'll do is it'll take the addresses from here, map them into locators, which it places there. So the outer headers always have locators, and the inner headers always have IDs. And that's, Noel coined the phrase jack-up model, because you're taking the protocol stack, you're jacking it up, and you're putting something underneath. And we always jack up the IP layer for many reasons. We ran it over ATM, we run it over MPLS, we run it over other types of IP tunnels like IPsec tunnels and GRE tunnels. This is nothing new. So this is what the header would look like for IPv4 when you encapsulate v4 and v4. The thing to note is that this outer header, when it gets prepended, this OH is the outer header, you have a source locator and a destination locator, and all the routers that see this packet have routes for these sort of, prefixes that they can route these locators on. And then we use UDP. UDP is really important. We switched from IP and IP to UDP because we want lags in core routers to be able to get good distribution over their members. So what we're going to do is we're going to have the router that actually prepends the header do a 5-tuple hash on these values like it does today, and that sent the source port based on that. So the lag will see then multiple microflows rather than one macro flow. One of the big disadvantages of IPsec today is if you get a corporation behind an IPsec tunnel, a lot of the service providers look at that as a 10 gig single flow, and they can't load split across lags. So we're going to fix that problem. UDP also has some capability of getting through firewalls a little bit easier. The rest of these fields and lists I won't talk about in detail, but they're used for a lightweight form of security, and these locator reach bits are used for locator reachability. Of course, the inside header that's built by the host are only EIDs. Very important. So let's go through an example. Let's say we have this site where there's a source and another site where there's a destination. Both sites are multi-homed. They're multi-homed to different providers. Say there's 4 providers altogether in this scenario. And let's say that these sites have been allocated provider-independent addresses. So we have 1/8 on the left-hand side and 2/8 on the right-hand side. What we're going to do is deploy only in the boxes you see listed there, LISP-capable functionality. The ITR is the ingress tunnel router. In other words, packets are going to ingress the tunnel at that point. And the ITR and ETR are going to have dynamic tunnels that they establish. They're stateless tunnels. Okay, there's no setup beforehand. They're completely stateless, datagram, best effort, what we know and love in IP. The ETRs are the egress tunnel routers. Now you'll notice that the egress tunnel routers, their locator addresses, in other words, the locator addresses that are associated with this site, is going to be 12.0.0.2 and 13.0.0.2. Those are going to be the IP addresses of those ETRs because they are attached to the provider to 12/8 and 13/8 respectively. Okay. Now what's going to happen is S is going to want to send a D. It does a DNS lookup, of course, on 2.0.0.2. That's what's in DNS. It doesn't know any difference if it's a LISP-capable site or not. It's just going to emit a packet that's going to be destined to 2.0.0.2, sourced by 1.0.0.1. Let's just say for right now that these ITRs have this mapping. What we have to do is have a mapping between this EID prefix and a set of locators. So those are the 2 locators. We're both going to use them because they have priority 1, and we're going to load split between routers D1 and D2. That's what the weight is, a percentage of traffic for each of the equal highest priority locators. So what's going to happen is S is going to emit a packet. It's from itself to 2.0.0.2. Okay, inside the IGP there, it's basically routing on 2.0.0.2. Nothing is changing in the IGP. So people will say, well, you are actually using EIDs as locators as well because you're determining what the location is within the site. And that's absolutely true. If we wanted to make the model or the semantic of EIDs and locators more pure, we would have to make more changes at the site, and we're obviously not willing to do that. We want incremental deployability. So that 2002 packet is going to flow through all the IGP routers at the site to the edge. They're going to follow the default route because 2002 is not a local destination. Let's say right now the shortest path from S to the exit is through S2. They're, in most cases, S1 and S2 originating the default route, and it's usually the shortest exit is going to be used for the egress packet. So S2 gets the packet, sees that it's an external destination, says, 2002 is an EID prefix. I need to look that up in the mapping database. This mapping database here says I need to prepend a header and use one of these two addresses. So it's going to choose 2002, and the packet's going to actually arrive at this ingress link through provider X. Now, it can choose to use 13002. It can hash. What's happening here is that the destination site is saying, I want to give you some control, Mr. Source Site, to be able to pick either locator that you want. But if I want it to be active backup, or I had another two locators, maybe I want for you to use 12002 and make 13002 priority 2 and only use it when 12002 goes down. But this policy here from the destination site is that I want you to load split traffic because I want active on these ingress links right here. So this guy, the S2 box goes ahead and he prepends the destination 12002. What he does he has to put in his own source locator in the outer header. Well, it's going to be the IP address that he uses for what his attachment point. So you notice, since he's attached to provider B, he uses 11001. Now, it turns out that D2 sending packets back can use 11001, or it can have a separate mapping entry to use S1 or S2 according to the source site's policy as well. So the packet then flows into the internet. All these BGP routers in the internet have not changed. They know how to route to 2002 and 11001. Those are all PA-based addresses or routable addresses. So we don't have to change the core routers at all. So the packet just flows through the policy, the BGP next, the best path selection path in each BGP router from this point to that point according to the existing policies within those ISPs. But we know, because it's destined to 12002, that packet will appear on this link in this site. That means that destination site has control on where ingress traffic comes. The only way it was able to do that previously is by injecting a more specific route. So the packet appears still encapsulated on that egress link to the site, and the ETR knows that 12002 is his own address, so it's a very easy hardware function to say, it's my address, I need a decap. He decaps and he delivers it into the site directly to the destination. That's basically LISP in the data plane. It's a map and encap scheme where it uses tunneling, where the outside headers are locators, the inside headers are EIDs. Now the big question is, what if that ITR doesn't have a mapping? I stepped back because I didn't want you to hear that, because that's the hardest part of the problem. So what if it doesn't have a mapping? It has to go get a mapping. It has to find out what the EID prefix, what are the locators for a specific EID prefix. Well, one way you could do it is you could data trigger it. Okay, so we've used many different techniques and we're experimenting to see which is the most robust and which is the least painful. So we can use a data triggered UDP map reply. What we can do on that ITR is we can copy the inner destination address to the outer destination address and send it on some alternate topology. Because if we send it on the real topology, we wouldn't be able to get it routed to the destination because that EID is not in the routing system. We're going to assume and force it to not be in the routing system. Okay? So if we decided to use the tools that we already have in the internet and maybe construct a different topology, and we run BGP, say over a GRE tunnel topology, we can actually have GRE advertise these EIDs if we wanted to. These would be addresses just like we know and love today, but these are prefixes that are aggregatable that are not tied to topology. They're tied to allocation boundaries. So they could be much more aggregatable than we see with the locators that are being currently aggregated in the internet today. So there's no mapping information that's being passed around in BGP here. It's just we're passing around NLRI that look like IPv4 or IPv6 addresses, but they're just a different namespace, and we don't cross the two namespaces. Okay? No changes to BGP for this. We can do this today. And we're about weeks away from prototyping this alternate topology thing, just to let you know. So another way we can do it is if there's no mapping in the ITR, we can use a control plane protocol, maybe something like cons. Dave will go into details about that, by having the ITR send a map request, and then the ITR gets a map reply that's returned back. And at the meantime, we'll have to drop packets because these fire hose of packets are coming to the ITR and it doesn't have a mapping, similar to a flood of packets that comes to a router for a directly connected host that doesn't have an ARP entry. The same sort of thing happens. We've gotten used to that over time, by the way. So this only happens the first time when a source site talks to a destination site. Any new sources talking to any new destinations at the same two sites, this packet drop phenomenon won't happen. So when people say packet drops, they get really scared, but it's really not that bad. Okay? But now, to be able to pay for that expense, what are you going to get in benefit? What you're going to get is a very good EID prefix allocation aggregation hierarchy that we're going to build. And we can force the aggregation to be very, very coarse in nature because, again, it's based on some alternate topology and not the physical topology. So we're able to make it very scalable. Dave will talk about it. We're calling it more of a pull model because you're going to go get the mapping that you need at the time you need it. Okay. Another way you can do it is you can there's two techniques called NERD and RPMD where you can actually have the information pushed. And if you push the information, the ITRs will never have a table miss. But it's at the expense of compressing this large data set and sending it to every ITR. Not every system in the internet, but only to the ITRs need this. We're calling this more of a push model. Okay. So we'll find out that, pull really doesn't scale, push doesn't really scale, so we have to pick one. So it turns out that what Dave's going to talk about is kind of a hybrid of both of them, where we're pushing and pulling at the right place, so to speak. Okay, prototype. So Cisco has done a LISP prototype implementation. We started it the Friday at Prague IETF when I couldn't get a flight out, so I was sitting there with Dave Bannister and Peter Schumacher, and I was coding. And so that's when it started. That was kind of fun. The OS platform is something Cisco's working on called DCOS. It's a Linux-based platform. And we're actually doing the testing on a one rack unit dual-core PC with 7 gig E's. We're doing the implementation on that. It's based on that 5th version of LISP. The very first internet draft of LISP came out in January. We're already on the 5th version, so that tells you we're working on something because we're finding bugs in the spec, we're trying to clarify, we're trying to add new features, so we're revving the spec quite often to keep people up to date on what's going on. This implementation is doing software switching only. We want to learn and experiment through this, and we're supporting both IPv4 and IPv6. What it supports is the ITR incap and ATR decap functions. We can load balance among multiple locators. We respect the priority and wait. You can configure multiple EID prefixes because we do anticipate that people are going to go get an EID prefix allocation, say from Aaron, and then they're going to misestimate and they're going to have to go get one later, and it's going to be out of a different power of 2 block, just like it's always happened. So we want to make sure that multiple EID prefixes that are not aggregatable because of that allocation can still be supported. We support locator reachability. Unfortunately, that's the coolest part of the proposal, and I don't have much time to talk about it, but the locator reachability stuff is done in the data plane. So you will be able to actually find out when a locator goes away faster than you would if it was in BGP. So what we're going to do now is relying on the BGP system in the core to provide solely reachability. We're not going to depend on it to switch over fast from one path to the other because the switching is going to be done at the endpoints. The endpoints are going to decide, the endpoints meaning the CE box at the site is going to decide that this locator's gone down, now I'm going to use this one. And the next set of packets that come, I can switch over very quickly. The implementation supports multi-VRF support because that alternate topology we're going to run BGP over GRE is going to be in another VRF. So we know that you can take 2 separate VRFs and they can be in separate addressing domains. So 10.0.0.1 here and 10.0.0.1 here are 2 different places, 2 different hosts. So we used the concept of multi-VRF to implement the multi-namespaces. And did I already say I supported IPv4 and IPv6? I wanted to make sure you guys really got that. We support both IPv4 and IPv6. What's next on the prototype? We want to implement crossover support. And all that means is we want to look at running IPv6 EIDs over IPv4 locators. Possibly LISP, at the same time it's doing a level of indirection, can be used as a transition strategy for IPv6 to IPv4. And then we'll look at, does it make sense to make IPv4 EIDs run over IPv6 locators? And which one we use is going to be the race. Will the host vendors be able to deploy quicker than the router vendors? That's going to be the test on which one of those are used, in my opinion. Since we have this level of indirection, hosts can actually move at different levels of movement. They could move very, very slowly, which a move could also be considered, I'm changing my providers because they charge me too much money, so I'm going to move to somebody else. That's a movement, but it's done at subscription time. Okay? Or you can be on a high-speed train with a handset moving. That's the hardest problem to solve in terms of mobility. So we're trying to figure out what part of LISP on that spectrum of slow to ultra-fast mobility we should try to support. But we've done some early prototyping on some schemes where there's no host changes for mobility, where we can use route returnability checks to protect against ITR spoofing. More to come on that as we get further down that design path. And then I'm planning on doing a cons implementation. Hopefully I can start it before the end of this month. Testing. I've been unit testing a course because Dave doesn't like when I give him broken code. So it's make before break. And then we started an internal pilot in about July. And Dave, the guys sitting up here basically, Dave, Vince, Daryl, and Greg Shepard has just joined. And they've been testing since 2007, setting up a pilot. And we are shooting for some kind of external pilot sometime in December. So if anybody's interested, please contact us. This was the unit test topology. All it's showing here is that these two boxes were the ITR and ETR. This is the smallest configuration you can get by with. I use Net10 and DFDF as EIDs, and these are two hosts. These are actually two routers acting as hosts talking to each other. What I tried to do is say, let's call that the site, and let's make it look like it's multi-homed to these two different locator IDs. So I made this look like the internet core and not the site, and then these guys are in capping. So that, once you get the code working, this guy decides that he has two locators to get the DR2 through this multi-access Ethernet path or this point-to-point Ethernet path. And so I was playing with multiple locators. As soon as the code compiled, that's what I started with. But then when the code was stabilizing, then the internal pilot testing was basically this. Dave's running an ITR, ETR now at U of O. He's got multiple locators that are there now that just come to the same box. He will soon put another physical box there so we could show different, oops, sorry about that. A different physical box there so we can show that we have two physical locations. Vince is actually testing at Cisco behind the Cisco corporate firewall, and we're trying to get packets through the firewall. That's been interesting. And I'm sitting here because I need to access, let's see, I'm sitting right here trying to access all these boxes to debug them. So very important is how do I go to a LISP site when I'm a non-LISP site? So we had to make that work day one, or we didn't have access to debug the code. Okay. I'm almost done. I have one more slide. And then Daryl is also there, but Daryl's interesting. He's not behind a corporate firewall. He's behind a retail firewall, and so he's been trying to get that to work, being behind Comcast. And Shep's out in the open. I shouldn't say that publicly, but so in summary, there's the draft. The cons draft is in 01 state, and the nerd draft is in 01 state. Please have a look at the drafts. We'd be glad to get your comments, and we will reflect them back into the specs. If you're interested in pilot deployment, please send mail to lispers@cisco.com. And I'd like to thank all these people that have really been part in a very detailed way in helping out with the effort. We thank you all. And LISP rules. We don't have time for questions?
I was going to say, since we've got data plane and control plane back to back, let's do questions afterwards, and that might help tie things all together.